I'd like to introduce James Brodman from Intel, who's going to be talking to us about some extensions planned to OpenCL through the command buffer extension. So James, over to you.
Thank you, Tom. So this is really work by Ben Ashbaugh and Ewan Crawford from Intel and Codeplay. For those of you who know Ben, I have slightly more hair than him. For those of you who know Ewan, I have much less hair than him. I will likely use the word we a lot in this presentation. I don't mean to imply that this is my work. I will use it more in the royal we sense, namely because I'm following the speaker notes. So this is, like I said, work from Ben and Ewan. The command buffer emulation layer, it's not an Intel product. We don't want to claim it is, but we think it's an interesting and useful tool for the SYCL and OpenCL community. And we also believe that the methods that were used in this work could be useful for other extensions in the future, just because they're not specific to the command buffer idea and extension in any particular form or fashion. So the crux of the problem that I'm going to talk about today is that the extension for command buffers in OpenCL was provisionally released in November of 2021, so about 2.5 years ago. And despite being a very useful submission pattern that's been used by graphics APIs like Vulkan or Direct3D or other compute APIs that may not be Khronos standards, recent data from the community-driven hardware database shows that only 2.5% of all reports in the database actually support the command buffer extension. And this is probably a lower bound because not all implementations have been submitted to gpuinfo.org. And indeed, most of the entries that are in the database are actually all the POCL implementation. But from this data, you can draw an overall trend, and implementation support for this extension that's been out for over 2 years still remains pretty low. So there are some other issues we can delve into about this and some things we can hopefully do about it. So this problem that I've just described is not unique to command buffers, and the community's seen this pattern with other extensions as well. Sometimes that extension can just take a long time to implement. And even after it's implemented, it can take a long time for the extension to really see deployment in the field in a lot of applications. And sometimes just some OpenCL devices and platforms may never support a particular extension. I mean, one such feature I can think of that may fall into this category is SVM from OpenCL 2, for example. So this lack of implementation of features really hinders adoption and kind of damages the developer confidence in a particular feature. Some applications may try to work around this and absorb the complexity by developing multiple code paths, one that supports a particular feature and one that doesn't. But in practice, most applications are going to cater to the lowest common feature set. And so a lot of these features never find use in applications today. So we need to figure out a way to kind of bust out of this cycle and find a way to make these features easier to use and easier to adopt, even if not all the implementations want to do the work in order to make it happen. So for this talk, we'll talk about how we've implemented support for command buffers using an OpenCL layer, which is a somewhat new feature to OpenCL that's been used in other APIs successfully. And through this, we'll show one potential way to kind of break the cycle of features never finding their path. So next, I'll talk about some prior work and describe why this command buffer emulation layer was implemented the way it was. So first, I want to talk about the OpenCL intercept layer, which is a project that Ben has been working on for many years that is useful for a great many things. And using the intercept layer is one way that you can emulate support for OpenCL extensions. In particular, we first prototyped support for unified shared memory in OpenCL and SYCL even by implementing this in the intercept layer on top of OpenCL SVM. And it's pretty straightforward to do this type of emulation in the intercept layer, since the way the intercept layer works is it basically, like the name implies, intercepts every OpenCL call. And once you're intercepting it, you can kind of then do whatever you want. So it could augment the existing APIs by adding support for new queries or performing bookkeeping that you need to support new features. Or you could just add whole new extensions entirely by just providing your own function that you can return from calls to CL get extension function address. So this is a functional solution, but it's potentially too heavyweight. It's kind of your nuclear option for supporting everything. And so we'd like to be able to do this in a lighter way that doesn't require as much effort from programmers or feature implementers. And this is where the layer concept comes in. So in the last few years, the OpenCL ICD loader has been upgraded to support the concept of installable OpenCL layers. And these layers provide another mechanism that you can use to intercept and augment certain OpenCL API functions. And compared to the intercept layer, it's a much lighter weight mechanism, and it's easier to kind of enable and disable individual layers. So far, most of the layers that have been written for this have been limited to things that like providing additional support for tracing or validation. So we think this is the kind of first effort to really add new functionality to an OpenCL implementation using this layer approach. And if you're curious to learn more about this layer idea and how it works in OpenCL, please see a tutorial from IWOCL 3 years ago. So we decided we'd try out layers, and surprise, it worked. So next we'll get into a brief overview of how this emulation layer functions. So most emulation layers generally have 3 classes of functions they're going to implement. The first one is really the most interesting and is a class of emulation function that adds completely new functionality implemented entirely within the layer. And these new emulation functions may call other OpenCL APIs, but they'll do so only in kind of support of implementing this new functionality. The second class of functions is what we call override functions. And these can add new functions to an API conditionally, but if that condition isn't met, it's just going to pass along the call unchanged. And the types of things that fall into this class will include things like query functions, where you want to add support for the new query attributes or IDs, but all the existing ones that are already supported, you'll just pass those through. And then that brings us to the third class of function, which we call bookkeeping functions. And these record useful information or implement some new functionality, but then they just kind of unconditionally pass the call along. So typically you're taking an existing OpenCL call, and just whenever you call that, you just want to make a note of what you did there. So with this knowledge, I'll now get into how the command buffer emulation actually works. So the process is reasonably straightforward. So when a command buffer is created, it needs to record each of the commands added to the command buffer. And this includes all of the arguments provided either explicitly or implicitly to all of the calls that get recorded. For OpenCL kernels, this could have been very difficult since we need to preserve all the kernel arguments set up for the kernel. But luckily in OpenCL 2.1, support was added with this API CL clone kernel that just solves the problem. However, using this CL clone kernel mechanism means that this emulation layer doesn't work on OpenCL platforms that only support OpenCL 2.0 or older. But since, like Kevin pointed out, most people are conformant now to OpenCL 3, this hasn't really been a problem in practice. Okay. So that's recording. What about playing back your command buffer? So after the command buffer is created, in queuing the command buffer simply just plays back all the recorded commands into the provided command queue. The command buffer emulation layer then needs to map the command buffer sync points to OpenCL events and may need to insert an occasional command queue barrier to enforce dependencies. But otherwise, the process is fairly fast and straightforward. So next, we'll briefly review things that went well while implementing this emulation layer and a few features that were challenging. So the good news is most things went well. The OpenCL installable layer mechanism is robust and performant. And the OpenCL API includes many features that make layering easy, like built-in reference counting for OpenCL objects, OpenCL object queries, and like I mentioned before, the ability to clone a kernel and its arguments. As for the command buffer extension itself, there were very few features that were difficult to implement. But there were some things that were a bit tricky. So one of the first features that was slightly tricky to implement in the layer was command buffer event profiling. We needed a mechanism to profile the whole group of commands inside the command buffer. But luckily, this problem wasn't too hard to solve by simply adding command queue barriers before and after the group of commands, and then using the events on those barriers for the event profiling. So we stick a barrier at the start, basically to measure the start and submit profiling for the command buffer, and for the completion, we use the barrier at the end. This does require us to track one additional event, since we have two barriers to deal with the start and the end. But this was pretty manageable and negligible overall. So this solution was a success. After we implemented it, our standard profiling tools allowed us to profile workloads using command buffers, both on the host and on the device. And so we have a little screenshot here of showing our, overall execution time for CL and Q command barrier, KHR. And then we can see that that gets, split up into a bunch of calls on the host as well underneath. But not everything was perfect. Some things were tricky. Error checking in particular was another problem that we encountered. The initial versions of the emulation layer omitted most error checking for simplicity, but when we started to use the emulation layer for more development and validation, turns out having error checking can be pretty valuable. It was especially challenging to perform error checking when commands were recorded into the command buffer, though, because the command buffer wasn't actually making any OpenCL API calls at this time. As a result, most errors were identified and the command buffer was enqueued, not when it was created. So we wanted to think of, can we do anything better here? So we did come up with a tentative solution. We didn't really want to replicate error checking inside the layer because we thought it would be error prone and complicated. So we tried to develop a solution that would reuse the implementation's built-in error checking mechanisms. Unfortunately, the solution still wound up being slightly complicated. So the way it works is kind of at setup, we create a test queue when the command buffer is created. And then we also create a blocking user event. And then we enqueue a barrier into this test queue that is dependent on this blocking event. So basically, we just have a train engine waiting in the station that can't go anywhere. And then once you start enqueuing things into the command buffer, they get enqueued into this test queue, but they never actually start executing because the thing is waiting on this event that is blocking. So that lets the native implementation's error checking mechanisms kick in for everything you're recording into the command buffer. And then when the command buffer is finalized, we set this blocking event to an error state, which causes all the dependent commands to be discarded. So basically everything we recorded into this test queue and the test queue itself can all be freed and kind of go away. So it gives us the functionality we want, but it's not cheap and it's a bit convoluted. Yeah. So this one we'll call a partial success. It worked and provided the requested error checking, but it didn't work well on all the implementations we tried. One implementation even printed unexpected and unrequested messages to the console regarding discarded dependent commands, which was a bit of a surprise. And so because of this instability, the functionality, it exists in a branch, and if we ever decide to merge it into the code, it probably won't be enabled by default. Okay. The final problem we encountered was command buffer state tracking. The command buffer extension describes 3 command buffer states: recording, executable, and pending. The recording and executable states are fairly easy to track and report, but the pending state is complicated because the command buffer emulation layer does not directly track command buffer completion. One possible solution to this problem involves tracking an event for each command buffer in queue and testing if it is complete, but this type of event is not tracked currently, so adding it would add complexity and overhead. The good news is that the emulation layer supports simultaneous use. So the value of the pending query, which is the tricky one, turns out to be kind of low, and it's unlikely that the state query implementation will affect real world code. Still, this is the one kind of feature failure we have in the CTS for the command buffer extension. So we'd like to fix this problem if possible. So next, we'll go into a few places where we're currently using this emulation layer for development and testing. So the first place we really saw a benefit from using this was in developing the CTS for the command buffer extension itself. By using the emulation layer, we could develop the CTS and debug it on any device and shorten the time to deliver CTS fixes because you didn't have to wait for a vendor to implement everything and test it themselves first. This improved developer efficiency, which was important because Khronos was working with a contractor at the time to develop these tests. As a bonus, the CTS found a few bugs in the layer as well. The layer has also been very helpful within the working group to prototype layered extensions, so kind of extensions layered on top of extensions. The command buffer extension itself was designed as a base specification, and it was envisioned that many layered extensions would add additional command buffer functionality. The layer currently supports the mutable dispatch extension, and we have prototypes for mutable memory commands as well. The mutable memory command prototype is currently helping to determine the best syntax for modifying memory commands. One final case where we're using the layer for feature development is in SYCL, particularly for the SYCL graph feature. The SYCL graph feature is an experimental extension to add basically the notion of command buffers, but at the SYCL level. And we're using the emulation layer to add this capability to OpenCL backends that we can map the SYCL API onto the command buffer extension. So it provides a convenient mechanism to develop, debug, and test SYCL work on top of OpenCL. And as we get towards the end, we'll take a brief look at the performance of the emulation layer, because features that add functionality but are very, very slow aren't always the best thing. So we identified 2 key performance questions that we wanted to answer. First, we wanted to determine if using the layer was expensive. How would an application perform if it chose to use the layer versus using a separate code path? Would an application pay a performance penalty, or could it see a performance benefit? For this test, we wanted to measure the submission time and the completion time and we wanted to be able to vary the number of commands in the command buffer. Second, we wanted to determine if the layer was effective. How would the layer compare to a native implementation? For this test, we wanted to measure the submission time and the completion time, and also to explore different execution scenarios like in-order versus out-of-order command buffers. So we developed micro benchmarks to answer these questions. So the primary micro benchmark we developed is a basic command buffer execution benchmark. It either enqueues n kernels directly into a command queue or n kernels in a command buffer. And this test can measure submission time or completion time. So we have some results on a bunch of different devices. We have an NVIDIA GPU, we have 2 CPU implementations, POCL and the One API construction kit from CodePlay. And we have both an Intel discrete GPU and an integrated GPU. And the key takeaway here is that using the layer didn't really cost you anything. The performance is about the same in both cases, which is a good result. So no penalty, great. We did see a couple results that were surprising. In particular, we'll call out 2. In the case of POCL, it was surprising because the emulation layer is actually outperforming the native implementation of the command buffers in POCL. And we reported this behavior as a bug. We don't think it should be faster, so we think there's probably something going a little screwy somewhere. For the One API construction kit, the results were a little surprising too. And the submission time results initially seemed too good to be true. But this is simply an artifact of the way it's implemented in the construction kit, in that it's basically just doing deferred execution of everything. So the submission has very, very low overhead, and you pay all the cost once you actually try to wait on the result. So in the first case, we reported a bug, and we found that the native implementation was faster in the other. So overall, the layer performance was acceptable. So now in conclusion, we like to think we've successfully demonstrated emulation of the command buffer extension with an installable OpenCL layer. We believe we've implemented almost all features, and the layer passes almost all the conformance tests, and its performance is quite acceptable. So give it a try, and please let us know if you find any bugs. And overall, we found the command buffer emulation layer to be pretty useful. It's being used to accelerate the development of layered OpenCL extensions and develop OpenCL CTS tests. We're also using it to develop features in SYCL and other models. And even when a native implementation is available, having the layer as an alternative implementation has been shown to have value. So, and finally, this notion of layers inside OpenCL we've found to be very impressive and very useful. It's very robust, performant, and capable. So we recommend other people start to write useful layers to add all kinds of new functionality for OpenCL and apply the similar techniques from this work into other extensions. So thank you.
Hi, James. Just a single question. Are we expecting implementers of the extensions to also implement the layers themselves?
That'd be nice.
Okay.
But you can use things like the layer to accelerate your own development, because you can use it for testing and comparison to make sure you're validating your results correctly.